All right.
Please.
Yeah, thanks everybody for coming back. I will start with a quick review of what we did yesterday, and then we'll go to some new topics about cold atoms. All of these things seem to be a little bit out of topic, but you'll see that there are fantastic analogies to relativistic quantum field theories and some problems even in black holes and high energy physics. So that's why I'm dedicating some time to it. It's a very educational exercise. So what did we do yesterday? I'll just summarize qualitatively and then we'll go back to the equations. And please, yes, actually the questions work out very conveniently. I can hear you very well. So if there is anything, just stop me. So the first thing is that we studied non-relativistic particles. We studied non-relativistic particles with a short range interaction. In fact, we even made this approximation of Fermi, where the interaction is very short range. And the range of the interaction is some little a. That's the range of the interaction. We saw that these non-relativistic particles develop emergent behavior, which is very difficult to understand just from the Schrödinger problem. So to see this emergent behavior, we took the limit of many particles where we kept fixed what's called the healing length, which is the product of a n to the power minus a half, where n is the density of particles in some container or a trap. So little n is the number of particles divided by the volume. So we took that fixed, the healing length. In this double scaling limit, we were able to prove that there is emergent behavior. This emergent behavior means that for very small momentum, so for particles with very small momentum, the dispersion relation or the spectrum of the Hamiltonian basically is given by the speed of sound times k. And we derived a formula for the speed of sound, which is given by the mass of the particles in the denominator, h bar in the numerator, and then the healing length. That was a nice formula that we derived. And we saw that this problem becomes semi-classical. We saw that this problem becomes semi-classical in this limit, even though the original the original Schrödinger problem is extremely complicated. So semi-classical in this limit. And the effective h bar was essentially 1 by n. Okay, so these are just the this is just a high level summary of what we did yesterday. And I'll just emphasize again that the fact that there is a speed of sound means that there is collective behavior and it behaves like a fluid. In fact, this phase is called a superfluid. This phase is called a superfluid. And we will talk a little bit more today about the fact that it's best to interpret this phase as a spontaneously broken particle number symmetry. So that's the particle number symmetry. That's particle number symmetry. Okay, so this is also why there is linear dispersion relation in a sense. We get Goldstone bosons for the particle number symmetry. Another piece of very important terminology is that these small k modes, these modes with very small momentum, which have linear dispersion, they are called in the literature phonons. Okay, and we obtain them by starting from the formula for a homogeneous superfluid and doing a mode expansion. So we started with a properly normalized homogeneous superfluid. Let me just check that I'm not messing up this formula. So we start from homogeneous superfluid. Yes, I messed up the sign, of course. It has to be like that. And then we add some small waves on top of it with some amplitudes, which are just oscillating in time, and a special profile, which is usual Fourier modes. Okay. So these are phonons. This is the theory of phonons, and we found their spectrum. Okay, so are there any questions about any of these four conceptual points from yesterday? Maybe I'll just remind before that, I'll just also remind that there was the story of Bogolubov, where MK was a mixture of creation and annihilation operators in quantum mechanics. In modern terms, we would say that since the U1 particle number symmetry is spontaneously broken, the excitations are not supposed to carry well-defined particle number symmetry. And that's why, even though the field operator psi started its life as a well-defined annihilation operator, because there is spontaneous breaking of the particle number symmetry, the modes don't carry well-defined particle number. That's because of this. So you could say that this is because of SSB, that we cannot use particle number symmetry to label excitations around the fluid. And therefore, MK can, in principle, be an admixture of creation and annihilation operators. Okay? Okay, any questions about any of these points? Okay. So, what are we going to do today? Today, we will study another type of excitations in this system. We will start today by studying another type of excitations. I'll show you another important excitation, which is not a phonon. I'll show you another important excitation, which is not a phonon. This is very important because you'll see that similar excitations exist in relativistic conformal filters, and they're important in the understanding of critical exponents. So we'll start by discussing another important excitation, which is not a phonon. It's not a phonon in the sense that it has higher energies. It has a higher energy. So it's not an immediate excitation of the ground state. It takes a little bit more energy to create this excitation. But this excitation has topology. It's kind of protected by topology. And that's why it's very important. And it's also observed experimentally in sodium atoms. And we will see that it's very important in the relativistic theories too. Okay, so this excitation, to explain the origin of this excitation, it's used to fix the following container. So we will put our cold atoms in a container, so we discussed so far, we were kind of not very specific about what is the container, because we assume that it's very large and we can just assume translational invariance. But for this excitation, the shape of the container is important. So we will take the container to be a three-dimensional cylinder, not a three-dimensional cylinder, full cylinder. So the boundary is a cylinder. Solid cylinder, that's the name. So the container will be a three-dimensional solid cylinder. Oh, three-dimensional solid cylinder. So the nice thing about this container is that it's axisymmetric. Axisymmetric means that we can use polar coordinates. And we will assume that this container is very large, and in particular in this direction, its size L will be some very large number. And in these coordinates, the radius is R. Okay? So we will study a cold gas inside this container, and we will discuss a new excitation, which is not phonon-like. So the excitation has the following. So the idea of this excitation is that let's look back at the homogeneous gas, just this fluid that we discovered. In the homogeneous gas, it's just oscillating in time, but there is no dependence whatsoever on the space coordinates. It's completely homogeneous. The next exit, and you should view these phonons as small waves on top of the fluid. So a very important conceptual point is that the full wave operator, psi, does not have any zeros in any of these modes, because you start from some big classical background, which doesn't have any zero, and then you add a small function on it. So this should be viewed they should be viewed physically. Phonons can be viewed physically in the same way as in sound waves. They should be viewed as density perturbations, because what they do, these phonons, is to change the density of the fluid just very slightly in some region of space, and then it propagates. And that's why they propagate according to the speed of sound, right? That's why this terminology is appropriate, because a small perturbation in density creates a sound wave. A more interesting excitation, well, sorry, I shouldn't say more interesting. Another type of excitation is an excitation where the full field operator has a zero. Okay, this is the excitation that we will discuss in this container. When the full field operator has a zero, it means that there are basically no atoms in that. It's not like you change the density by a tiny bit compared to some classical density. So we start from some classical density proportional to this mu. But here, we will actually take the density to zero at some point. So at that point where there is a zero, there's just the density goes to zero. So it's not a phonon. You actually just look for excitations which have absolutely no particles at some point in space. Okay, so the ansatz, that's why the axial symmetry is convenient. You can do it probably in other geometries, but in the axial symmetry case, it's very convenient because you just write the following ansatz, which is axisymmetric. So you still assume that there is more or less a uniform density, but there will be some profile, which depends on the distance from the origin. And we're going to put a zero at the origin by adding an angular dependence. That's what makes it topological. Theta. Theta is the azimuthal coordinate. That's just the azimuthal coordinate. So for this function to be well defined, for this classical solution to be well defined, of course, chi will have to go to zero at r going to zero. Well, let me just write r equals to zero to make it less mysterious. Chi will go to zero at r equals to zero. And that means that there is a simple zero for the wave function, and there are no atoms. It's just a hole in that sense. And you could put any integer in front of theta. So we could put any integer in front of theta. Let me just do that for completeness. We could put an integer s, which is an integer, And that will describe a zero, which is somehow a higher order zero, a zero of order S or something. So we can look for such solutions. Are there any questions about this ansatz? Good. So for the normalization of this wave function, we will need to require that chi-squared integrated over r dr times 2 pi times L. Oh, let me divide by L. That will be a much more sensible thing to do. I'll put 1 by square root of L. So that chi-squared is just a properly normalized function in the polar coordinates in R2. So I'm just going to require that is equal to 1. Okay, that's just yeah, that in our conventions, you remember that we scale the wave function by the number of particles. So that's the proper thing to do, remembering that the coupling G turned into G prime. So we use that G prime for the four-body interaction in this normalization. Okay, so it's a mathematically well-defined problem to solve, and psi has to satisfy the equation of motion, the classical saddle point equation that we found yesterday. That is basically that Gross-Pitesky equations, the Gross-Pitesky equation that we discussed yesterday. Okay. So such solutions cannot be found analytically, but they can be easily found numerically. Such solutions can be easily found numerically. I'll explain now what the main properties of these solutions are. So easily found numerically, such solutions are called superfluid vortices. Second, something went astray. They're called superfluid vortices. And typically, what you find is that this function of chi vanishes, but then quickly, as you go further away from the core of the vortex, it goes back to a constant. It goes back to a constant. And this constant is going to be the same as in the homogeneous superfluid. So the effect of the vortex dies off somewhat quickly as you go further away from the core of the vortex. So what is the asymptotic value of this function chi? Anybody wants to suggest what's the appropriate asymptotic value for this function chi, so that we return back to the homogeneous solution at large enough distances? Anybody wants to suggest what should the asymptotic value of chi be? Let's the pi r squared. So comparing to that, yes, we want to compare to that solution. Oh, we want to compare to this solution, right? Yes. So therefore, the asymptotic value reached here is r times square root of pi, in such a way that the normalization agrees with the normalization of the superfluid. It's just the square root of the volume pi r squared. Okay. And here it goes to 0, of course. And the question is, what's the distance? If you solve these equations numerically, or if you do some back of an envelope estimates, you can try to understand what is the distance scale over which this vortex basically becomes indistinguishable from the ordinary fluid. And the answer is that it's exactly the healing length. That's why it's called the healing length. It's the size of the vortex, essentially. It's the distance at which the vortex becomes indistinguishable from a homogeneous superfluid, essentially. Okay. Now, some very important properties of this excitation are the following. I'll mention a few properties of this excitation. One is that this excitation has angular momentum. Also, phonons have angular momentum. Well, phonons have momentum k. And if we go to azimuthal coordinates, they will have angular momentum, as usual for particles with momentum. But the vortex has a very large angular momentum, much larger than any individual phonon. So individual phonons will have angular momentum over the order of h bar. It could be h bar, 2h bar, 3h bar. The angular momentum of one of those vortices is very large compared to a phonon. We can compute it from the Noether theorem. So we can find a formula for the angular momentum by starting from the action and applying the Noether theorem to obtain the angular momentum. And we will find that it's essentially an integral over the whole volume r perp r squared, and then the density of particles times the mass times the velocity. This is literally just the high school formula for angular momentum. We take the mass times the velocity times the distance, and this is the volume divided by L. We don't integrate over the direction L. And actually, this can, even if you don't know the exact solution for chi, because you need to put it on the computer, the angular momentum can be evaluated exactly. That's because if you write, you need the formula for the velocity in quantum mechanics. And as you remember, this is just a derivative of the wave function, anti-symmetrized. So actually, this integral can be evaluated even without RDR times 2 pi. It can be evaluated even without knowing the exact solution. So we just need to take the wave function, take some theta derivatives, and anti-symmetrize it like that. And now a small miracle happens, which is that when you take the derivative of the wave function, you just act on that piece. And then the integral that you have to evaluate is that of chi-squared. But we know the integral for chi-squared. It follows from the normalization of the wave function. And therefore, this can be evaluated exactly. And after some algebra that you can do carefully, you'll find h bar n. So this is a small check you can do. So this object has protected, well, has a very large angular momentum. This is the total number of particles. This is the total number of particles in the container. And h bar is the natural quantum for angular momentum. And that's more than any single phonon. Any single phonon will have 1 h bar, 2 h bar, 3 h bar, as I said. And this is a very large angular momentum, and it can be exactly calculated. Oh, I should have said that we can put back this parameter s. It affects the angular momentum in a very simple way. So I'll put it in parentheses. If you put back this parameter s, it just multiplies the angular momentum by s. Okay, for a vortex that's not the elementary vortex. Okay, so the angular momentum of this object is protected and it can be calculated. The second property that I want to discuss is the energy of the vortex. You might expect that the energy of this vortex is very large because it has a lot of angular momentum. So certainly it should be very large compared to phonons. And here's a very important physics idea that you'll see coming back in many relativistic theories too. So we can try to estimate the energy of this vortex by just integrating the kinetic term. So let's remember that the action had a kinetic term for the wave function, which looked like grad psi squared. That was one of the contributions to the action. And it was integrated over RdR times 2 pi. And there is also L from the integral over the volume, since nothing depends on L. And then there is also h bar squared over 2m. And there is also some factor of n. because of the way we normalized the wave function. And a very simple argument here says, look at the components of the gradient. So we look at the components of the gradient which are in the theta direction. So the energy from the swirling of around the vortex is kind of large. Maybe I should have said here. Maybe I'll make another comment about the angular momentum. So you can ask, where is this angular momentum coming from? It's coming from the vortex, which creates a zero density at some point, but also there is a velocity around it. So the superfluid is just like an ordinary fluid can circulate around when there is a tornado. A superfluid can do the same. So you can calculate that the velocity at which the superfluid circulates around the vortex decays like 1 over the distance from the core of the vortex. So there is a lot of velocity that goes all the way to the boundary of the system. And that's why there is a lot of angular momentum in this fluid, because there is essentially some velocity even far away from the vortex, even though it decays algebraically. This creates a lot of kinetic energy. So when we calculate the kinetic energy from this contribution, this is quite large because there is a lot of velocity in the system all the way to the boundary, and you get an integral like RdR, I'm just approximating it, times L. But here, this is the angular velocity of the fluid. So you actually get 1 by R squared. Okay? Just from this. You get 1 by R squared from the velocity. And this integral diverges logarithmically. And that's a very important divergence that happens in Nambu-Goldstone bosons and in 2 dimensions and many, many other applications in physics. So it goes like the logarithm of the system size, regularized by the healing length. Because why are we putting the healing lengths in the denominator? Because that's more or less where the vortex heals. And this approximation begins to make sense. So the exact formula for the energy, a more precise formula for the energy, I'll just write a more precise formula for the energy for future reference, putting back the h bars. It's h bar squared times the density of the superfluid times L divided by m times the logarithm of R by C. That's approximate. To actually calculate the energy, you need to do some numerics, but that's how it scales with the density and the other parameters of the system. So a vortex costs a lot of energy, and in fact, its energy is logarithmically divergent in the system size. So for an infinite system, vortices are not excitations, but for finite systems, they are excitations with large angular momentum. Are there any questions about that? Oh, sorry, before that, I'll just say that this is why you'll often hear people saying that vortices are not excitations in infinite systems. It's because their energy diverges logarithmically. But at least for finite systems, there are certainly such excitations, and they've been observed in the laboratory, even in sodium atoms. Okay. Are there any final questions about this? Are there any questions about the vortices in superfluids? We discussed their energy, angular momentum, and I'll just say that experimentally to observe them, people take this container and they start spinning it with some angular frequency omega. And then in a rotating reference frame, the energy becomes h minus omega Lz. And if you rotate the container fast enough, vortices begin to appear, because while they cost a lot of energy, they also carry a very large angular momentum. So they actually minimize this Hamiltonian for sufficiently large rotations. And so people have already been able to achieve the appropriate frequencies to excite vortices. And sometimes, if you rotate it fast enough, you'll get a ton of vortices everywhere inside the container. So that's how the vortices are created in the lab. by just spinning the container. And by spinning it faster and faster, and more vortices can be created.
Yes, I have a question.
Yes.
Is it possible to numerically find solutions that has more than one zeros? It would mean that there are multiple vortices, and I'm not sure how this feature would work then.
Can you just say the question again? The reception, yeah, I didn't. The volume was a little bit too low.
I'm saying,
Take your mic. Take your mic.
hi, yes.
Yeah. Oh, now it's excellent. Yeah.
Is it possible that there are solutions which has more than one zeros?
Yes, certainly. There is a big science of trying to find solutions with multiple vortices. So I can say a few words about it. Is that your question about solutions with multiple zeros? Is that essentially the question?
Yes, exactly.
Right. So what you need to know the following thing. So vortices, you can ask, let's suppose you have a vortex is a thing like that, right? It's like a little tornado. And the velocity decays algebraically away from the vortex. So if the vortices are spinning in the same direction, they repel. If the vortices spin in opposite directions, they attract. Okay. And using that, you can sometimes balance the forces in very interesting ways. So there is a particular configuration of vortices, which is like a triangular lattice. And it has the repulsion between, the attraction between vortices exactly balances the centrifugal repulsion. So what people found experimentally is that when they spin this container with some frequency omega, which is large enough, it gets populated with vortices, okay, everywhere. And the vortices form a very nice triangular lattice. So the vortices sit on a lattice, some nice triangular lattice like that. And the vortices attract each other, but they sit in a container that's spinning, so there is centrifugal repulsion and the forces exactly cancel out. So you can read about this lattice on the internet. They've seen it experimentally. It's called the Abrikosov lattice, a triangular lattice of vortices. But you can also look for solutions of vortices even without spinning by trying to balance these forces. And there are various interesting solutions that you can discuss. By the way, does this remind anybody of something, that vortices of similar spin repel and vortices of opposite spin attract? Does it remind you of something? Anybody has any idea of what that's similar to?
Magnetic fields?
Yes. So this reminds a little bit of electromagnetism. In fact, there is a duality between the theory of vortices and particles with Coulomb interactions. There is some kind of duality, but I'll probably not get to it in this course. Okay, any more questions about vortices before I move on? Well, I'm going to move on now to the relativistic theories and the applications of semi-classical techniques in relativistic theories, where all these things will be somewhat important. Any final questions about the cold atoms and vortices? Good. So now we're going to the relativistic theories. So I'll give you some, the context will be conformal field theory. That will be the setup. We will be discussing strongly coupled conformal field theories, and we'll be using semi-classical techniques to make predictions about their properties. And the discussion will be in this course in 2+1 dimensions, or you can think about it as 3+0, because we'll often work in Euclidean signature. And I'll focus on one particular model. Just because it's the simplest model where all these ideas can be exhibited. I'll focus on this model in the first maybe two in let's say in what follows. I'll focus on this model, but I'll get to ADS-CFT and black holes a little bit later. For now, we'll just focus on this one particular model, which is called the O2 model. And to explain what the question is, I'll give you a quick introduction to what this model is and where it appears. Just a second, I'll get, so that I don't make any mistake with the conventions. I'll just pull out. Okay. Okay, so where does this model appear? Let's start from, I'll explain where it appears. There are three places in physics where this model appears, but they're kind of it's more general than just this model. This is how we obtain interesting conformal filters in physics in general. So one place where this appears is in the study of lattice models in 3 Euclidean dimensions. This goes back many years. So for instance, we take a 3-dimensional lattice. I cannot draw a 3-dimensional lattice, but imagine a 3-dimensional lattice where on each side we have a vector in R2. This vector is called S. I is the lattice side, and S is the vector in R2. Let me take the vector to be unit normalized. So I'll also assume that S squared I is 1. Okay. And the lattice model has the following Hamiltonian. So all we do is we force these arrows to be preferentially in the same direction if they're aligned. So we force them to be preferential in the same direction by adding a coupling minus J times the cosine of the angle between SI and SJ. And then we sum over all the I and J, which are nearest neighbors. So this notation means nearest neighbors. This is what this notation means, nearest neighbors. Okay, this is a version of the Ising model, and this is the cosine of the angle between two unit vectors. Okay, it's a very simple 3D lattice system. At finite temperature, we just calculate the partition function, which is the sum over all the possible configurations of these unit vectors with e to the minus h beta. E to the minus beta h, where beta is the inverse of the temperature, essentially. So this is some function of beta and j. So we obtain some function of beta and j. This is just the usual Gibbs ensemble. Gibbs or Boltzmann. This is the usual Gibbs or Boltzmann ensemble. Okay. And what you find out when you put it on the computer is a remarkable fact, which is that there is some critical beta. There exists some critical beta where the system is in a second order phase transition. You find the second order phase transition. So that means that the partition function becomes non-differentiable in the infinite volume limit. The partition function as a function of J and beta becomes non-differentiable in the infinite volume limit. And for instance, if you study the correlation function of S at some location I and S at some location J, this becomes some power law, which measures the distance on the lattice with some critical exponent. Also, if you study other observables, you get various other critical exponents. So you can, for instance, you can ask, let me just erase that. So you obtain various critical exponents at the phase transition, and the correlation length diverges. So if you denote by Xi, not to confuse with the healing length, the correlation length, it diverges. That's another critical exponent for just the correlation. The correlation length diverges. And that gives another critical exponent because then the correlation length as a function of beta is 1 over beta minus beta C to some other critical exponent. So this critical exponent and these critical exponents are some, numbers that we can measure on the lattice, and they're part of the data of the conformal field theory at beta C. So that's one way in which this model arises. This model has a global O2 symmetry. That's why it's called the O2 model, because you see the energy functional. The energy functional is completely invariant under the rotation of all the spins at the same time by some O2 transformation, because that doesn't change the cosine of the angles. Okay, so that's one way in which this model arises from a Euclidean lattice model. Another way in which this model arises is from just a field theory. We take an action, which we integrate over space, which is Euclidean in this case, and we have a complex field. We put derivatives, we do the square, and then we add some quartic interaction, and this flows to some critical point. This flows to some critical point with conformal symmetry. Okay, so lambda flows to some critical point, lambda star. And lo and behold, you get the exact same critical exponents as in the lattice model. So that's just a continuum version of the lattice model. I should stop now. Are there any questions about these two ways in which the O2 conformal field theory can arise? Are there any questions about the lattice model or the Euclidean field theory? Okay, and the final way, which is maybe a little bit more recent, maybe you did not see that in your courses, is that it can arise from a quantum phase transition. That's maybe the most popular way nowadays because people have a lot of simulations and there is real-time dynamics. So here, it's really 2 plus 1. You study a quantum system in 2 plus 1 on a lattice. On each lattice point, you put a spin 1 degree of freedom. And you had some interactions, which are like S dot S across nearest neighbors. And you tune the coupling constants in such a way that you flow to a critical point at 0 temperature. So there is a critical point at 0 temperature for this type of, it's a Heisenberg type. It's a Heisenberg type antiferromagnet. So that's I won't go into that because it's not essential. But that's experimentally the most relevant way in which people simulate this model nowadays, especially if you're interested in real-time dynamics and not just in Euclidean properties. So this model arises from lots of applications. I didn't even mention all of them. It also arises from gauge theories in 4 dimensions near the chiral symmetry breaking, phase transition, and deconfinement transitions, etc., etc. So it has lots of applications. But the problem is that it's a strongly coupled model. Let's think about it in this language. The critical point is at strong coupling, and we really don't have analytical control over correlation functions at the critical point. It's very strongly coupled. Correlation functions contain these critical exponents, and all we can do is to put it on the computer or try to use some bootstrap techniques which can bound the critical exponents. So I just wanted to quote a few of the critical exponents that we know so that you see that there are actual numbers in the game. Let me just quote a few of the critical exponents. What? I'm getting there. Okay. So here are a few critical exponents that I took from what's measured in the literature and from some bootstrap literature. Let me just get it straight. Here it is. So when we calculate the correlation function of this complex field phi at point x and the complex field phi at some point y, we obtain 1 by x minus y. And the power here is called 2 delta phi. That's a typical behavior in a conformal fixed point that correlations decay only algebraically. And we find numerically, or from simulations or from the bootstrap, that this is 0.51. Similarly, we can calculate correlation functions of phi dagger phi at x, phi dagger phi at y. We find another critical exponent, which is often called epsilon. And we find that this is approximately 1.50. It's maybe 1.501. It's very, very close to 1.5. There are more digits, of course, both here and here. And finally, maybe just for your entertainment, we can also do phi squared x, phi squared y. That gives another critical exponent. It will be somewhat important later. That's why I'm quoting it. Sometimes this one is called delta t, because the word T stands for tensor, because this is like a rank 2 tensor in the U1 case. And this I didn't write for myself in the notes, but I think it's 1.2 something. Please somebody verify on the internet if somebody can verify, but it's roughly 1.2 something. So we don't know if these numbers are algebraic or rational. These are like fundamental constants of nature that appear from these many, many different problems in physics, this zero temperature antiferromagnet, or the lattice model, or the field theory model. These are some fundamental numbers, these critical exponents, and we don't really have any way of calculating them ab initio. That's remark number 1. And secondly, we don't know their properties really as numbers. We don't know if they're rational, algebraic, transcendental, and we don't have a systematic way to obtain them. That's also, I think, fair to say. So these are you can think about the collection of these critical exponents You can think about this collection as some kind of fundamental constants of nature. And we have no access to them, to be honest. Now, the notion of universality is very important because almost all the systems with O2 symmetry, so all of the systems have O2 symmetry. All the systems with O2 symmetry with critical behavior likely will end up in this universality class. So that's why these numbers are they're not model dependent. They're really just some abstract fundamental constants that appear in lots of physical systems because of the idea of universality. That when there is a phase transition of second order, many different microscopic models might look the same. Okay, are there any questions about this set of numbers, which are these critical exponents in the O2 model, or their properties, or how they were computed? Any concerns about that? Good. So now I'll tell you the main problem that has appeared recently. So some people are frustrated that we don't know how to calculate these numbers ab initio. But people have made the following very interesting realization, that this model has operators which look like that, with some n, which is n could be 1. We covered the case of n equals 1 here. N could be 2. We covered this case here. But n could also be 1,000,000, okay? And the question is, what are the scaling dimensions of these operators when n goes to infinity? This is a question that you could ask because we don't really know anything about the low-lying ones, but maybe we can use semi-classical techniques to understand very heavy operators. These are sometimes called heavy operators. Just a second. These are sometimes called heavy operators. And their U1 charge is little n. So they're heavy operators and they're heavy charged operators. Heavy and charged operators. So an idea that became very important recently is to ask, can we really say something analytical about the large little n limit? So can we, for instance, make predictions for numerics? Numerics has become sufficiently strong that people can easily go up to little n equals 20 now. We have actually numerical data about little n equals 20 or so. And so it would be really nice to make theory meet experiment or numerics by solving analytically the problem at very large little n and then trying to match with numerics. Okay, so this is the problem that I'm going to describe. I'll start describing it today and we'll continue for the next couple of hours. A similar problem that we'll then discuss is what happens to operators with a huge spin. So another construction with very large quantum numbers is maybe when you take an operator like phi dagger phi, but you put a lot of derivatives here, acting on left and right. So L could be again 1, 2, but it could also be 10 to the 6. So these are the spinning operators. And the question is there a semi-classical technique to understand the large L limit? These are similar problems in a sense. And again, there is a lot of numerics. Here there is numerics up to L equals 100 or so. So there is a lot of stuff to compare to. Okay, so that's the topic that we'll discuss in the next couple of hours of what is going on in the strongly coupled conformal filters in the sector with very large quantum numbers, large charge, large spin, heavy operators. Okay, is the question clear, or are there any remarks on it?
Can I ask a question?
Yes.
Where comes the U1 charge?
Mm-hmm. That's an excellent question. The question is, why is the U1 charge important? Is that your question, essentially?
Yeah, and also where does it come from? Like, we're we looking at a O2 system. So I hypothesize that the charge should be attributed to O2 symmetry. So
Yes.
where one comes from.
Right. Okay, so let me explain where it comes from and why it's important. This is a very important question. So let's look at the field theory description of the O2 model. Okay? So here phi is a complex field. That's why I put here phi is a complex field. And that's why in the action I put absolute value squared here. Okay? Now, the O2 symmetry, O2 is the symmetry of this model. You can see it in the action because you can take the field phi and just change it by any phase that you want. That generates SO2. But you can also complex conjugate the field. And these two operations together give you O2 symmetry. Is that clear of how it acts?
Yeah.
Good. Now, therefore, operators like this, phi to the power n, they would carry SO2 charge little n. This is the U1, which is the same as SO2. So when you take a complex number, like a complex field phi, and you raise it to a large power, its SO2 transformation will be with charge little n. Now, so that's just the kinematics. These operators, by contrast, are neutral under SO2 because they have phi dagger and phi. So they only have angular momentum because of the derivatives. But these operators have U1 charge or SO2 charge little n. Okay. Now the question is, why is it important to consider operators with charge? Okay. So this is actually that question is difficult. You could ask, why am I discussing the O2 model and not the Ising model? In the Ising model, the field that is the fundamental field phi is real. So you can discuss operators like phi to the n, but they don't carry any quantum numbers. I don't even know what I mean by when I write phi to the n, because it's not really distinguishable from phi to the n minus 1 and some, Laplacian of phi or something like that. They don't have quantum numbers that make them distinguishable. So the purpose of the reason that we're discussing the O2 model here is because when I write phi to the n, there is something concrete that means, which is that it's the lowest operator. Of course, this is a composite operator. It requires renormalization. But when we write phi to the n, we maybe should put quotation marks here, because what we really mean, it's the lowest operator. By lowest, I mean smallest possible, smallest critical exponent. It's the lowest operator with Q of SO2 being little n. So phi to the n is just a way of writing somewhat imprecisely that we're interested in the lowest lying operator with some very large SO2 quantum number. Is that clear?
I think so.
Yeah, while in the Ising model, there is no such thing. I don't know how to even ask the question in the Ising model very clearly. There are lots of heavy operators in the Ising model, but there is no real analog of a quantum number that can allow us to ask what is the ground state among some very heavy operators. So maybe the picture to have in mind is that there are some low-lying operators. This is delta, okay? These are the scaling dimensions of operators in full formal field theory. There are some operators, but then it becomes very dense. There are lots of heavy operators. In fact, there is exponentially many of them. It's 2/3. The number of operators in some window grows exponentially, like the exponent of the scaling dimension to the power 2/3. So there is no hope that we will ever actually find, one of those operators with the exact scaling dimension and with the exact microscopic description as a renormalized operator. I believe this will never happen. We will never actually find these operators because there are just so many of them and they're so close by. These are the microstates of a black hole in a sense, because there are exponentially many of them. So what is special about the O2 model is that we also have charge. So actually we have delta, but we also have charge. So for charge equals 0, for 0 charge, we have some low-lying operator, and then there is a dense mass. For charge equals 1, we have some low-lying operator and some dense mass. Okay? And let me continue that. For charge equals 100, there is some low-lying operators and then dense mass. Okay? So what is special about the O2 model is that we have this quantum number Q. And what we're trying to do is to find these guys because they're isolated from the continuum. And that's why this problem is very nice. We're not trying to find one of the haze in the haystack. We're trying to find the lowest lying operator with some given charge Q. And that we might hope to achieve in our lifetime. While to find an actual microstate in the exponential when it's exponentially dense is probably completely hopeless. So that's why we're focusing on the O2 model. Of course, we can also add spin. Spin is another quantum number. So we will be looking for the lowest lying operator with a given spin. We're not going to try to find the needle in the haystack, but we're just going to try to find the lowest operator with a given spin, analogously to this problem with charge. Is that clear? Or are there any questions about this general philosophy?
We expect to have some degenerate operators in terms that they have the same scaling dimension or the same width, like the difference between scaling dimension and spin.
Are you asking about like in the haystack, in this dense region? Are you expecting to find degenerate operators or among the ground states?
Also in the ground states, low energy.
I mean, I don't really expect that there will ever be a degeneracy because the exact mathematical degeneracy cannot come for no reason, right? Do you agree with that?
Yeah.
Yeah. So we don't expect any exact degeneracy in the haystack, neither in the ground states, I would say.
Okay.
Now, another thing to say is that where is the bootstrap? Bootstrap can, numerical bootstrap is a very successful technique. What does the bootstrap do for us? It can cover small delta and small q and small j, small angular momentum L. So using the bootstrap, we can find some of these states here, okay? But the bootstrap is not useful for very, very large Q or very, very large L. Neither is the bootstrap useful in this region where there is a haystack, like exponentially many operators. We will never distinguish them, I believe. We will never find a way to get to the core of these operators. So we just have to resort to some averagings or something like that. And so this technique that I'm going to describe today is really complementary to the numerical. I'll start describing it today. It's really complementary to the numerical bootstrap because it goes for the ground states, but large Q or large L. So it gives complementary results. Maybe I could make a plot like that. If this is Q and this is delta, bootstrap is here, just to give you a roadmap of what people have done. And also Monte Carlo, Markov chain, and also DMRG. DMRG is the quantum version of simulation. All the simulations are around this region. Here, there are maybe dragons. By dragons, I mean, it's something like a black hole. There is an exponential number of states and it's just hopeless. Here, there are some semi-classical techniques. Here, there are some semi-classical techniques, and here there is nothing. There are no operators here, because operators with very large Q should have some large enough delta, okay? So here we expect nothing. Here we expect semi-classical techniques, and here it's just probably hopeless. So that's what I'm going to explain in these lectures, these techniques that apply somewhere for the ground states of operators with large quantum numbers. So these states. Okay, So is the roadmap more or less clear? This is all for the O2 model, but of course, it's obvious to you that it applies for n equals 4 super Young meals, or even in the ADS-CFT context, or it applies in many other phase transitions of importance in condensed matter and statistical mechanics. So any questions before we dive into the general logic? That's the most important part of the lectures, to understand, perhaps, that this is the question. So if there are any more comments about it, it's time. That's the time to ask. Okay. So what is the main idea what is the main idea? We want to learn about the scaling exponents of some very complicated operators or very heavy operators, like these guys that we discussed here, like this guy and this guy. And we spent like 2 hours discussing cold gases. And in cold gases, we learned some technique to understand the energy spectrum of complicated quantum systems. But here we're discussing not the energy spectrum of a quantum system. We're discussing scaling dimension. So perhaps the most important idea is that you can think of the scaling dimension of a quantum system as the energy of an auxiliary quantum system. Auxiliary quantum system. So the first step to get started is to translate the questions about scaling dimensions of primary operators in conformal field theory, or of operators in conformal field theory, not necessarily primary, to a question about the energy spectrum of some quantum system. Because we already know how to use semi-classical techniques for quantum systems by trying to go to large particle number or large charge or some large density. So that's the first step. Let me explain this step. How much more time do I have today? Just wanted to explain this step at least.
Half an hour or something, or maybe a bit. Yeah.
Okay. Good. So that should be enough to explain this and to give you some first estimates. To give you some first estimates of what's going on. So I have to explain what is this auxiliary quantum system. So here's how the logic goes. The scaling dimension is the eigenvalue not under time translations. Usually we think about the energy as the eigenvalue under time translations. The scaling dimension is the eigenvalue under dilatations. That means that we take all the coordinates, multiply them by some number, and we take all the field operators and multiply them by some other number. Okay, so that's how dilatations act. They just rescale space and time, and they rescale the field operators, and they rescale all the composite operators. So the question is, how can we turn such a transformation? How do we turn this? We have to turn this transformation to time translations. We will try to turn this transformation to time translations for some new time. So it will be some auxiliary quantum system with a new notion of time, and we'll do a change of variables to do that. So it's quite clear how to do that. Essentially, what you see is that you're rescaling space and time. So let's say in Euclidean coordinates, we have x1, x2, x3. When we rescale all the coordinates, what we're also doing at the same time is that if we define the distance from the origin as r, then log R would transform like log R plus log lambda. And that looks a lot like that. So this is the seed idea of what's called radial quantization. Why did I take the logarithm? Sorry, I have to explain why did I take the logarithm. Log R varies from minus infinity to plus infinity. And therefore it's like a good notion of time. Log R is like an alternative notion of time because it varies from minus infinity to plus infinity. So you may have heard about radial quantization. That's basically the idea, to think about the logarithm of the distance as a new notion of time. And under that new notion of time, there will be a radial Hamiltonian. There will be a radial Hamiltonian, which basically does that time evolution, that new time evolution, and the eigenvalues of the radial Hamiltonian, are going to be exactly the scaling dimensions. So that's what we want to achieve. We want to write a quantum system where this is true. Now I'll show you how to do it technically. So now I'll show you how to do it more technically and more precisely. Are there any questions about the general idea of what we're trying to do and why? Why are we trying to find this auxiliary quantum system? Are there any questions about it? Oh, okay. So how is it done technically? We start from the metric of R3, which is dx1 squared plus dx2 squared plus dx3 squared. We next write it in spherical coordinates, where we have dr squared plus r squared times the metric of the two-dimensional sphere. This is the metric of a two-dimensional sphere. Next, we do the following trick. We pull r squared out of the metric. I haven't done anything yet. I'm just rewriting it in a convenient way. And now comes the maybe most important point, which is that we see that the original metric on R3 and the metric here inside this term, they only differ by a prefactor, which is space dependent. It's a prefactor that depends on your location. But the main idea is that this factor just changes the overall scale of the metric. In particular, it does not change the relative angles between small tangent vectors. So because this only affects the overall scale of the metric, if you have a conformal field theory in which there is no scale, everything is algebraic, this should drop out. So the main point is that at the fixed point, at the CFT, and only at the CFT, it's not true outside of conformal field theory, r squared can be dropped out, and you obtain the following metric. I should not write equals, I'll just write similar. And this is only in conformal field theory that you can get rid of this overall prefactor, because otherwise the theory does depend on the overall scale. And this can be furthermore written as d log r squared plus d omega s2. So this is essentially an infinite line. This is just an infinite line times a two-dimensional sphere. So we have a two-dimensional sphere times time. So this is the time, and this is the sphere. So what we obtained is that the quantum system, we started from conformal field theory in infinite volume, but now we are instructed to study a quantum system on a two-dimensional sphere. Let me just put the radius of the sphere to 1. We found that a quantum system on a sphere, I'll just restore the radius instead of 1. We found that a quantum system on a two-dimensional sphere of radius r, you can set r equals 1 without loss of generality, if you want, because it's a conformal filter, it doesn't care about the scale. A quantum system on a sphere S2 of radius r calculates the scaling exponents. Okay, this is a remarkable fact that is behind the recent breakthrough of this fuzzy sphere. So for ages, people were not able to calculate critical exponents precisely because you have to go to long distances and evaluate these algebraic exponents. But if you do a quantum simulation directly on the sphere, it just calculates the scaling exponents for you. This is the main idea behind the recent, maybe you heard about the fuzzy sphere algorithm. It's a numerical algorithm to compute the scaling dimensions. And it utilizes this idea that a quantum system on the sphere just spits out the scaling dimensions of the original conformal field theory. Are there any questions about this statement? Yes. Good. Therefore, we reach a nice conclusion that the scaling dimensions of these complicated composite operators are energy eigenstates of this auxiliary quantum system. And furthermore, there are the ground states with a given fixed charge. There are also the ground states at some given fixed Q equals little n. Okay, so that translated the problem of understanding critical exponents at phase transitions to looking for ground states of quantum systems at some large charge. And that should remind you a lot of our discussion of cold gases, because what we did is we studied the ground state of the system with n particles. And here we are instructed to do something analogous. We have to study the ground state of a quantum system with total particle number little n. And little n could be a very large number, like 10 to the 6 or something. So it's a relativistic version of particle number. Our discussion at the beginning was for non-relativistic particles, a Schrödinger problem, essentially. Here, this is a relativistic. So I'll just write it. This is a relativistic analog of our discussion of cold atoms. Okay. So that's how we're going to think about it. And we're going to use similar techniques to attack this problem. So before I just leave 10 minutes for general questions, I'll make one claim. And this claim I'll repeat again next time because it's a somewhat difficult statement, and I'll try to explain it in several ways. So I'll just make one final statement. I'll use general principles to try to estimate the energy of such ground states with fixed charged little n. And the logic will be similar to what we did in the non-relativistic theories. So let me just change the notation here. I want to change the notation and to appeal to an analogy with the non-relativistic theories. I want to change this notation a little bit because I want to use the notation that's more similar to what we did in the non-relativistic theories. So I'm just gonna call it capital N because that's analogous to particle number. Okay, So I'm just going to make a physical argument now, then leave 10 minutes for questions, and then we will justify it more as we go on. So here is the main argument. By now, this argument can be seen to is understood a little better and also seen numerically, and also holds in the ADS-CFT correspondence. So can somebody reminded me, in the non-relativistic theories, what was the energy of the ground state of a system with some number of particles and some interaction range little a? What happened in the non-relativistic theories? Does anybody remember? What was this is what this NR stands for. Let me just write it as proportional. Anybody remembers? Say again, please. Yes, it was proportional to the density. Squared. It was proportional to the density, right? Sorry, let me just remember the notation. It was A times little n, right? Here, yeah, so here we're going to use dimensional analysis to guess the answer. So we have a system on the sphere. So let's just use some just general physical argument. We have a system that lives on the sphere with radius r. And the total charge is n. So let's calculate the charge density or particle. Let's calculate charge density. This is the charge density. This is capital N divided by r squared. I hope everybody agrees with that. So this is the charge density. Now, we will use the same logic as the non-relativistic theories, that the energy should be only a function of density. Well, we will basically use the same. I mean, we will kind of and the energy density I meant. So the energy density, we will use the fact that the energy density is only a function of the local charge density. So just write it as epsilon. We kind of use locality to say that if we have some charge density little n on the sphere, the energy density should also be only a function of little n, because we are assuming some kind of equation of state. That's basically the same as what happened in the non-relativistic gas, where it was the energy density was only a function of the local density. So we have to try to guess what function is it gonna be based on dimensional analysis. So here we're going to use dimensional analysis because it's a conformal field theory. In a conformal field theory, there is no scale. There is no scale. So if there is any formula whatsoever that makes sense, it's gotta be correct up to some constants. So energy density, what are the dimensions of energy density in a relativistic theory? It's well, of course, energy divided by r squared, divided by distance squared. That's the units of energy. But energy in relativistic theories is the same as 1 by distance. So that's the same as 1 by distance cubed. These are the dimensions of energy. On the other hand, density, what are the dimensions of density? It's a number of particles per volume. So that's 1 by distance squared. So the only formula that makes dimensional sense, lacking any scale in the problem, is to put 3 halves, if I'm not, with some constancy. That's some constant. Okay. So therefore, now we know the energy density. We can obtain a formula for the energy as a function of n. So that's, I'll just put squiggles. Energy is R squared times energy density, which is proportional to R squared times n to the power 3/2, which is proportional to R squared, and then I'm using the fact that density is n over R squared, which is proportional to n over R squared to the power 3/2, which is proportional to 1 by R times n to the power 3/2. Therefore, on a unit sphere, let's now go back to the unit sphere. We get a prediction that energy goes like the U1 charge to the power 3/2. That's the SO2 charge. And that's the scaling dimension. So that's the scaling. So we get a remarkable prediction that I'll put on a diagram that we have the same diagram as before with various values of Q. And we see the ground state will have to become like that. And then there are some excited states. And then there is some haystack of operators. So we obtain this kind of qualitative picture that these guys here should behave like Q to the power 3/2 if we measure their scaling dimensions on the lattice, for instance. Okay. So this is the main first prediction that comes from assuming. What did we assume to obtain this prediction? What did we actually assume? First of all, we assumed, well, we just remembered that we're dealing with a conformal field theory. But the main assumption is that energy density is a function of the local density only. So that's locality. And I think this is the only assumption. Okay. So I think this is an extremely generic prediction that should be true in pretty much every quantum system. Check. I'll just make 2 remarks and then for questions. Check. It's true for black holes. If you consider the extremal black holes, with some charge Q, their mass goes like Q to the power 3/2. It's true for in the O2 model, which we can see numerically in simulations. It's true in various large N models that people have solved since, and probably in many others. So we obtained essentially with no cost at all a generic prediction for the scaling dimensions of operators that look like that. So we obtained this prediction. And you see that unlike free field theory, so I should say that in free field theory, this is not true. In free field theory, this is true, but what I wrote is not true. So this is in free field theory. Free field theory is an exception for many reasons. Probably this is true as soon as there are any interactions. And you see that it leads to very large deviations from free field theory. Instead of growing linearly, it grows like Q to the power 3/2. Okay, here I'll stop if there are a few questions about the topics today. We'll continue from here tomorrow.
Yes, hello. So I have
Hi.
a question about the comments that you made at the end of the superfluid vortex arguments. So you said that there is some sort of electronegativity that happens between the repulsive and the attractive case for vortices. Is there a central case, and in that case, can we work out the BPS bounds for this system?
Okay, you're asking about the analogy between vortices and electric charges, right?
Yes, exactly.
And the question is if there is a what was the question? If there is a precise analogy or it's only
The question is, if that duality can be made precise, is there a self-dual case for this system? And is there, in that case, a BPS bound that can be found for the energy, for instance?
yeah, excellent. So the question is about this. So this is a little bit beyond what I was planning to teach, but I can give you the keywords if you'd like to learn about it. So this story is the beginning of what's called vortex particle duality. These are charged particles, okay? You see that vortices behave like charged particles in electromagnetism, right?
Yes.
And indeed, people made a really big deal out of it. In a sense, in some superfluid theories, the duality is really precise. That electromagnetic particles behave like vortices, and the spins match, and the energies match. You remember I calculated the spin. So yeah, it's a very nice story that works out. Um, in fact, there is a very interesting interpretation of this in the electromagnetic language. That's essentially the calculation of Dirac of the spin of a diode, the spin of a system where there is magnetic charge and electric charge at the same time. So there is a very elaborate dictionary. Many things seem very similar. And if you are even more sophisticated and you add some supersymmetry, this is just the beginning of the story that's called mirror symmetry.
Okay.
So, yes. So it's a very, very well developed field, but I was not planning to explain it. I just wanted to show you that some simple calculations already lead to something that looks very appealing.
Thank you very
Sorry, should there be what?
Hi, sorry. I have a question. So, why did you apply the radial quantization on R3 here?
Oh, so
I
I decided to show you how semi-classical techniques work only in 2+1 quantum or 3+1 Euclidean. And we applied radial quantization here.
Okay. So, because the critical exponent from this argument heavily depends on the dimension, it will be typically d+1 by d, I guess.
Yes. You mean the final answer? Like the
Yes,
very,
yes.
very final answer will be
Yes.
yes, you're 100% right. Yeah, so the very, very bottom line, which I presented only in 3 dimensions here, it's actually in general dimensions, it's d+1 by d, where d is the number of space dimensions, not space-time.
And so, in this radial quantization picture, where did the O went into?
Like it could be any OM, right?
You disconnected from the microphone after the first 10 seconds. You said in this radial quantization picture.
Yes. How is the 2 of O2 coming in? It could be any ON. No.
It just means that, so yeah, I'll repeat that next time. It's kind of, radial quantization is an idea that you can obtain scaling dimensions by studying the spectrum of some system that lives on a sphere. Is
Yes.
that, okay, that's the general
Yes,
idea. Now, if the original conformal field theory had an O2 symmetry, then this auxiliary system that lives on a sphere has an O2 symmetry as well. And therefore, the quantum states of that auxiliary system can be labeled by their O2 charges or SO2 charges. And Q is essentially the SO2 charge of an eigenstate of that quantum system on the sphere. So that's why I'm using SO2. If there is no SO2, there is no charge to talk about. Like in Ising, there is only a Z2 symmetry, and I really cannot use semi-classical techniques. There is no sense in doing that. But here we have this sequence of operators with increasing Q, and we can discuss the ground states at large Q. So that's the thing that I'm utilizing here.
I see. So, for example, if this was a O3 model, then there will be two charges.
Exactly. So of course, I'm presenting the simplest possible example with just one conserved charge, and I'm looking at the ground state for that given charge. You're absolutely right. You could study the O3 model or O4 model, or you could study n equals 4 super Yang-Mills, right? Which has O6 symmetry.
Yep.
And then you could try to find the ground states or how their scaling dimensions behave for different choices of these Qs. And there are many limits in which some Qs become large. And people have not exhaustively understood it. There are just a few cases that we understand.
Okay, thank you so much.
Yeah, so that's why the O2 model is really ideal for my purposes. It shows the main ideas and it's the simplest.
Okay. Hi, I have a question on the last point of today, namely the energy SO2 charge to the 3-half, no? And we obtained this in the CFT example. You commented that this is not an assumption yet. So how can you comment on a way to relax this result and make it more general for out of the CFT assumption? I would say you could like define out of diagonal terms in the metric that could take into account like the rescaling outside a conformal theory. But,
Yes. Outside of conformal filter, there is no notion of scale of critical exponents, of course, you understand, because the correlation functions don't decay algebraically. Here, you see, I'm trying to solve a very concrete problem. I'm trying to just understand these critical exponents that appear in correlation functions when they decay algebraically, like here. So I'm trying to understand these critical exponents. Now, outside of conformal field theory, the correlation functions are far more complicated, far more complicated. And like you'll have to tell me like a more precise, you'll have to tell me what kind of problem are you interested in if there is no conformal field theory, if there is no conformal symmetry. When there is conformal symmetry, I can identify this space of critical exponents, which is some infinite dimensional space of all the operators. And I can try to measure them, or I can try to, like understand their physics. Outside of conformal field theory, it's just far more complicated. There is many more moving parts. So tell me what exactly are you interested in, for instance?
okay, so
Depending on the model you are interested in, you can find further simplifications
to define
results out of the conformal point.
Yeah, I mean, it's of course very ambitious and nice idea, but it would be very difficult to say something super general. By contrast, I think this thing that I showed you today about how scaling exponents behave, just giving this crude argument, I think is super general. And well, it doesn't work in free field theory, because in free field theory, this assumption breaks down. In free field theory, you don't have like a local equilibration or emergent behavior. This kind of just means that there is some emergent behavior and the ground state becomes like some sort of fluid or maybe Fermi surface. But in free field theory, none of that. In free field theory, this doesn't happen. So I think this assumption is super weak. It just requires maybe locality and maybe some interactions. And it just seems to always work. While if you go away from conformal field theory, I wouldn't know exactly what kind of general statements you could make.
okay, thank you.
Yeah, but it was not proven though. I should say that this is not proven. It just seems to follow from simple physical principles like that there is a locality and interactions that equilibrate the system. Yes.
I've actually had a similar question, but now I see that it might actually relate as a comment. So isn't it true that maybe criticality is also important here as an assumption, since if I remember correctly, criticality is also quite related having things like energy density, for example, not being dependent other things, but just symmetries themselves, like intricate symmetries, not like coupling constant and whatnot. So my question prior to your discussion with colleague, with Leonardo, was why did we choose to look at theories that exhibit some phase transition, and where does this phase transition come from? I'm guessing the O2 is not the symmetry that's being broken. I would like to hear more about that. Why this?
Yeah. Okay.
Yeah.
First of all, your first comment was 100% correct. In general, the relation between energy density, the energy density and particle density could be super complicated. Here, it just took this very simple form because that's the only equation of state that you can write down if you have no other dimensionful parameters. But you're 100% correct that more generally, if you're outside of conformality, the equation of state could be pretty much anything. And we wouldn't be able to say much. For instance, we still don't know the equation of state inside a neutron star because it's just too complicated. Okay, so that's for comment number one. For comment number two, why am I discussing this O2 model? Maybe I'll just go back to that to explain why is it a good warm-up example. So here I wanted to say that sometimes the O2 model is also called the XY model. So if you look at condensed matter literature, they actually refer to it as the XY model also. So the O2 model for me does a few things. One, it's strongly interacting. It's a strongly coupled model. O2 is global, unbroken. And you're right about that. It's an unbroken global symmetry. So it serves as an example of a strongly interacting quantum system with some global symmetry that's unbroken, and we can make some predictions about it using semi-classical techniques. Even though we cannot make predictions about low-lying states, for that we use numerics and etc. We can make analytic predictions about excited states using the semi-classical techniques. Two, the reason I chose this model is because it's very famous, so it's omnipresent. It appears in StatMech. It appears in CondMat. It appears in the dynamics of gauge theories at finite chemical potentials, etc. It just it's a model that a lot of people have worked on, and being able to show some new results about this model is impressive because it's something that people spent a lot of time with. So these are the two main reasons I decided to take this model. It's also the simplest, yes? It's also the simplest model because it has just O2 symmetry. So this is the reason I'm showing you the results for this model, but the techniques are very general, and you could discuss many other things with the same ideas. Is that okay? Is that an answer to your question? Can you just take the microphone?
Is it working? Okay.
Yeah, it's working perfectly. Hello? Yes, I cannot.
We have a Q&A session.
Yeah, maybe if you try to.
Yeah, I can hear you.
Many times
Yeah.
the is it important? We want theories to have that.
Are there important theories to have what?
Phase transition. So
Yes. So yeah, like the whole discussion is focused at the phase transition. That's because there you obtain conformal symmetry and the equations of state simplify. So I only did that because the equation of state simplifies at the phase transition, and you could make concrete predictions. Outside of a phase transition, the equation of state is just as you said the equation of state could be anything. But at the phase transition, the equations of state super simplify, and the theory remains very strongly coupled. So it's a nice situation that you can have something.
I think this is an assumption because I believe this strongly. Then in
Yeah, somehow the microphone goes in and out, so somehow I can hear you very well at some point, and then it snaps, and I cannot hear anything anymore.
Last question.
Yeah, I can hear you though, because you.
Is my understanding, is this understanding correct? We have the correlation function phi x phi y with the scaling dimension 0.51, and
Yes,
then and in the next case we had 1.50.
yes.
So as we increase the number of phi's, we'll slowly approach 1.5. Is that correct?
Oh, no. The scaling dimension goes like the number of phi's to the power 3/2. So when you take q to be like 100, if you had 100 phi's, it would be 100 to the power 3/2, so which is 1,000.
Okay.
Yeah,
Okay.
so
Yeah.
the main thing here, which is shocking, is that in free field theory, the scaling exponent of q powers of phi is just q. Well, it's a half q, to be honest. Here we see that it grows much more quickly because of interactions.
Okay. Yeah.
So what I'm going to do tomorrow is to show you in more detail what happens at large Q, and we'll obtain a slightly more precise prediction about large Q. And then I'll show you also some agreement with data. That's the plan for tomorrow.
Do you want to ask it?
Yeah, if there is one more questions, go ahead. Yeah.
Comment a bit more about why for extremal black holes we should see this
Q to the 3.5 scaling.
You're asking why should we see it?
Yeah, so
is it guaranteed that
all of these states would correspond to, or these operators should correspond to extremal black holes.
That's an excellent question. So I'll say that this is maybe a very important question. We see that extremal black holes obey the same formula, that their mass goes like their charge to the power 3/2. Let me just give you a more concrete answer. Let me see if I'm gonna cover that later on. Yeah. So we see for now that some general arguments suggest that that's how the scaling exponent should behave as a function of Q. And we also know that extremal black holes have the same feature, that their mass goes like u to the power 3/2. And you could ask, does that mean that these states are actually black holes? You could ask, does that mean that this is a black hole? Is this an extremal black hole appearing in the O2 model? Okay, that's your question, right?
Yeah, because you also made the comment that black holes should correspond to the top region or like the region
extremal,
above.
extreme. Sorry. Yes. Yeah. Let me just clarify. It's super. I need to make a very important clarification of this plot here. So this region has generic black holes like Schwarzschild black holes. Here we get formulas which are very similar to extremal black holes. So this region where we find the ground states at given charge, these are the low temperature black holes, according to Hawking's calculation of temperature. These are the black holes whose temperature goes to 0 because they're the ground states of some quantum system at some given charge Q. So they should not have temperature. While these are the black holes which are generic. Is that distinction clear?
Mm-hmm.
Okay. Now, one very important thing is we should discuss, are these states really extremal black holes? And that is one of the main topics of the next lecture. I'll show you what we know. We know a lot. We know this state now. We understand it. We understand its few excitations here. Of course, we don't understand the haystack. The haystack is as mysterious as it ever was, but we understand the few excitations here of this state. I'll try to show you that these are not black holes. So in the O2 model, they look like black holes in terms of some simple formulas like scaling dimension, but I'll calculate the entropy of the states and I'll calculate their first few excitations, and you'll see that these are not black holes. So these semi-classical techniques make a very clear prediction that extreme black holes are not the right answer. And
if you go to a different model, can you find a black hole, or
I
what's the
believe
difference?
I believe that black holes are just never the right answer. It's an approximation. Well, I think the community now believes this, everybody in the community now believes that extremal black holes basically don't exist. They're an artifact of the classical approximation in general relativity. If you take quantum corrections into account, extremal black holes go away. So it looks a lot like black holes, but I'll show you more concretely what we know about the states. I'll show you that what we know agrees with numerics, and these are definitely not black holes. They have a smaller entropy, and they have completely different excitations.
Okay, thank you.
Okay, so we can postpone other to tomorrow if it's like quick one. Otherwise,
Yeah, if there's one more quick question we can do today, and otherwise tomorrow. Yeah.
Yeah. So if each phi carries a O2 charge, then if we are trying to determine the scaling dimension of phi to the n, then so this basically is the representation of a parent algebra is n times O2, right?
Yes.
So this similar thing can be reproduced using, if you are, let's say if you are looking at a large number of n, then it's basically large n matrix model, right?
Okay, okay, keep going.
Yeah, that's all. Yeah.
So you want to see an analogy, between you want to say that these states here are described by a large n matrix model. This
Yes.
too cluttered already. Okay,
Yes,
it's a great, brilliant idea. We actually in supersymmetric theories with O2 symmetries, this has been shown.
Oh, I see.
But beyond supersymmetry in this O2 model that today we're talking about, I don't know how to show that, and I don't know what is the matrix model. In supersymmetric theories, it turns out that for some BPS operators, what you said is just exactly right. You can obtain a Q by Q random matrix model, where Q is the charge.
Yeah, yeah.
But beyond supersymmetry, I don't know how to show that, and I don't know if it's true.
Okay, thanks.
okay, so thanks. So we'll have the next lecture at the same time tomorrow, so 4 p.m. here and 10 a.m. for Zohar, and we will have a Q&A session before. So Zohar, if you are able to connect, say from 9 a.m., it's up to you. You can let us know. Otherwise,
Yeah, I'll be there. I'll be there.
Okay, great. Thanks.
Okay.
Okay.
Thank you. Bye bye. Have a good dinner, everybody. Bye bye.